Okay, so in this video we'll be solving this problem, which is a very simplified air conditioning system. Basically, you have hot air coming through a pipe over here, and it will be exiting at a temperature of 22 degrees Celsius, but it's going at 32. So basically the air is getting cold. So what do they use in order to cool it is refrigerant 134A, which comes in here as a mixture and probably is going to come out over here as a superheated. But again, that's my educated guess. But we'll see. So we have other data on the sketch, and what we need to solve for is what is the mass flow rate of the refrigerant, so the mass flow rate of the air in kilograms per minute, and we need to find what is the rate of heat transfer in kilojoules per minute between the air and the refrigerant. So basically, how much heat has been removed from the air. Okay, so I'm going to redo this figure on the page because to redo the figure for me is part of the solution. Okay. Okay. So we have here our system in which we're going to have the pipe of air coming this way, and then we have the pipe of refrigerant coming this way. So let's see. Let's say this will be the air. This is 1, 2, air. And we know it's at 1 bar, temperature of 32 degrees Celsius, which is 305 Kelvin, with a volumetric flow rate of 30 cubic meters per minute, and it's exiting almost at constant pressure, 0.95 bar at a temperature of 22 degrees Celsius, which is 295 Kelvin. Okay. On the other side, we have refrigerant, which is coming in at 3 and 4. So this will be refrigerant 134A. So coming in at a pressure of 5 bars with a quality of 0.2, which is 20%, exiting at the same pressure, but at a temperature of 20 degrees Celsius. And okay, so let's say this would be M sub R would be the refrigerant. So basically we have M sub 3 will be equal to M sub 4, which is the mass flow of the refrigerant. And same way we have M air, so we'll have mass flow of 1 equal to the mass flow of 2, which will be the mass flow of the air. Okay, so what do we need to solve for? We need to solve for the mass flow rate of the refrigerant. So for MR in kilograms per minute, and we need to solve for Q between air to refrigerant 134A in kilojoules per minute. Okay, so let's get started over here. Let me zoom out so that the whole page will fit on the screen. Okay, so first thing I will do is what type of problem are we dealing with? This is a problem where you have mass flowing, entering and exiting, so this would be a control volume or open system problem. So for this control volume, we can write the first principle of thermodynamics. That will be what? Heat transfer minus the work going inside the control volume plus whatever is going in. So we have air, mass flow of air, H1. Also we have refrigerant, refrigerant H3. And what is leaving? We have air leaving at the state H2. And we have refrigerant leaving at 4. So from this figure, you see that there is no heat transfer and there is no work being added or removed. So basically we are left over with M flow of air H1 minus H2. I'm moving that one to that side. Now move the mass flow of the refrigerant to the other side, will equal to what? H4 minus H3. And here we need to solve for the mass flow of the refrigerant. So mass flow of the refrigerant will be equal to the mass flow of the air times H1 minus H2 divided by H4 minus H3. Okay? Okay. Or we could solve it here, so it would be equation 1a. Let me go to another page. Or knowing that the air is an ideal gas, we could say that the change in entropy will be equal to M Cp delta T. So in our case would be what? Mass flow of refrigerant times Cp times T1 minus T2. Okay? So that equation 1a can be written as mass flow of R will be equal to the mass flow of A times, okay, we're trying to solve that, so we already move it to the other side, so it will be M Cp T1 minus T2 divided by H4 minus H3. Okay, so basically all we are saying is that the difference in enthalpy H1 minus H2 will be equal to Cp T1 minus T2. Okay? But we'll solve the problem both ways, see if there's any difference or not. Okay, so now in this problem we need to find what would be the enthalpies. First maybe let's try to find what would be the mass flow of the air. So we know that the air, again, is an ideal gas. So if it's an ideal gas, we know we can use the relation PV equal RT. Okay, so if you look at the figure, at 1, we know even the volumetric flow rate. And what is the definition of the mass flow? Would be M, so it's of air, will be equal to what? Volumetric flow rate at 1 divided by specific volume V1. So what we can do is solve the top equation for V. Let's say V1 will be equal to what? R T1 divided by P1. And we can substitute over here. So I will have the mass flow of A will be equal to volumetric flow rate at 1 divided by R T1 over P1. Or we could just say that A will be equal to P1 times volumetric flow rate divided by R T1. Okay. Okay, where R over here is the universal gas constant divided by the molar mass of the air. Okay, so let's do this calculation. So from table A1, we find that the molar mass of the air is the first one is equal to 28.97. And the value for the R constant is 8.314, is even given at the bottom of the table. Let's see if I can zoom in. Okay. Or it should be on the unit page. Okay. So it's 28.97, and the universal gas constant is 8.314 kilojoules divided by kilogram Kelvin. Okay, so let's see if we can do the numerical application for M. We have mass flow of A of the air will be equal to what? P1, which is 1 bar, so we know that I'm running out of space, so 1 bar is what? It's 100 kilopascals. 1 pascal is Newton meter square. So let's see, we have P1 to be equal to 1 bar, so it would be 100 kilopascals. Okay, 1 pascal being Newton meter square times the volumetric flow rate, which is given to us as being equal to 50 cubic meters per minute, divided by R, that will be 8.314 divided by 28.97. Units are kilojoules per kilogram Kelvin times T1, which is equal to 32 degrees Celsius or 305 degree Kelvin. So I don't know what to do with the units. So basically you see this kilo will cancel with this one. Then okay, what is 1 joule? is 1 Newton meter. So this is 1 Newton meters. So newtons will cancel with the newtons. We have meter square times meter will be cubic meter, will cancel with this one. Kelvin will cancel with this one. So we are left over with kilograms per minute. So this will give us here that m sub a is equal to 57.122 kilograms per minute. Okay, so out of that equation we have m. Let's try to find now H4 and H3. So H3 and H4. So remember that H4 and H3 now, we're talking about the refrigerant 134. So at H3, at point 3, we know it's a mixture. So we know state 3 is a mixture. So in order to find those values, we then need to go to table A12, which is for the refrigerant, and we look at what pressure at P3 equals 5 bars. So if you want, let me try to do a little figure. So TV would probably be the easiest one. So we are on a line of constant pressure, which is 5. And initially we are somewhere over here. Okay? So I'll try to find here where this is. X3 is given to us as equal to 0.2. So we go to table A12, we look at 5 bars, and we're going to look at the value here of H fluid and here H gas. And then we're going to have to use the equation to find what is the value for 20%. So we go to the table A12. I'll show you that now. We find out what is HF, H gas, HFG. So let's go to table A12. Okay, so this table is in kilopascals, so 5 bars will be 500 kilopascals. And let's see what we should get. So at 500 kilopascals, we get for HF to be 73.32, HFG 186.04, and HG 259.36. If I write this down, we get 73.32, 259.36, 186.04. And we know that X3 is equal to 0.2. So we can write down that H3 will be equal to H fluid plus X3 H FG, which is equal to what? 73.32 plus 0.2 times 186.04, which gives you H3 equal to 110.528 kilojoules per kilogram. Alright, so now for H4, okay, so for H4, H3, H4, what do we know? We know at state 4, we know the pressure is still 5 bars and that the temperature is 20 degrees Celsius. So from the same table as before, or from another one, so table A12, let's see, at 500, what was the saturation temperature? 15. So at 500, you see that the saturation temperature is 15.71. So what does that mean on the figure? That means here that the temperature here along this line is T saturation. So at this point we have T saturation is equal to 15.71. So it's the line where it's constant. However, we know that the temperature is 20. So what does that mean? That we will be somewhere over there. So we'll be on the superheated region. Okay? So H4 basically will be over here. But what is most important is that we know that we need to go to the superheated tables. So that's table. So state 4 is superheated. Okay, so we go to table A. I think it's table 13. So, okay, they keep changing everything. So we know P2 is 5 bar, which is 500 kilopascals, which will be equal to 0.5 megapascals, and we know that the temperature is 20 degrees Celsius. Okay, so if we look at the table, we need to look at 0.5 and the temperature of 20. So we'll have that H4 will be equal to, what's the temperature? Let me check again. Is 20 degrees. So H4 will be equal to 263.48. So table A13 at 20 degrees, H4 is equal to 263.48 kilojoules per kilogram. There we go. So now we are here. So let's go back to the initial equation. So we have this, we have H4 minus H3, and now we need to use either this equation here that we're going to call 1b, or we can use the equation right here, which will be 1a. So let's try to do it both ways, okay? So we need to look at what is H1 and H2, and then we can figure that out. So now let's say we're going to find, let me go to the next page. We're going to find H1 and H2. So there's two ways to do it. One would be to go to table A17, okay, which is this one over here. And what do we know about the temperature at point 1? Temperature at point 1 is 305 Kelvin. So if we go to the table, 305, we are lucky, they give us that value will be 308.22. We can say from table A17 at T1 equals 305 Kelvin, we'll have that H1 is equal to 305.22 kilojoules per kilogram. And that at T2 equal to 295 Kelvin, we'll have that H2 to be equal to what? So 295 would be, see if I can zoom in a bit more, would be 295.17. Okay? So 295, so H, so 295.17. 295.17 kilojoules per kilogram. All right. So if we do that calculation, you get what? So we need to find the relation, which is H1 minus H2 will be equal to 305.22 minus 295.17, which would give you H1 minus H2 equal to 10.05 kilojoules per kilogram. Okay, but we could have done as well. Remember, we said that H1 minus H2 should be equal to Cp, or more or less equal to T1 minus T2. So where can we find Cp? So Cp will come from table A2, which is over here. So let's take it at 300 degrees. So we see that Cp will be equal to 1.005. So table A2 at 300 Kelvin, we have that Cp is equal to 1.005 kilojoules per kilogram Kelvin. So we just substitute, what do we get? H1 minus H2 equal to 1.005 times T1 was equal to 305 minus 295. So in this case, we're getting exactly the same thing, but that's not the case every single time. They will be close, but they will not be really identical. This gives us 10.05 kilojoules per kilogram. Okay, so now we can go back to either equation 1a, which is this one here, 1a, which is this one here, or 1b, this one here, to solve for the mass flow of the refrigerant. So let's say we can use from either 1a or 1b. What do we get? Mass of refrigerant is equal to the mass of air. So let's say we use the H1 minus H2 divided by H4 minus H3. So what do we get? Mass flow of refrigerant will be equal to, what did we have for the mass flow of A? 57.122 times 10.05. H4 we had 263.48, and H3 we had 110.528, sorry. So if we do the numerical calculation, we get that the mass flow of air will be equal to 3.753 kilograms per minute. Okay, so this problem is being quite long. Alright, so the last thing we need to do is what? We need to determine the amount of heat that is removed from the air. So I'm just going to do on this figure over here, okay, I'm just going to plot the pipe of air. So I could do, this will be the air, okay, and then all this stuff here will be the place where you have the refrigerant. So in this case, I'm going to have here 1, 2, and then this time I'm going to select as my control volume this one over here. Okay, this is my control volume, and what we need to find is what is the amount of heat that goes from the air to the refrigerant. So it will be our Q dot, and here will be M of air, H1 and H2. So now again, we're going to rewrite the first principle of thermodynamics for this control volume. So we have Q dot minus work control volume power plus M of air H1 is going in, will be equal to the mass flow of air H2 leaving. In this case, again, there is no power in or out, so we have that Q will be equal to M of air H2 minus H1. Okay, so if you do the numerical calculation, or actually we could write down what? This will also be equal to what? MA CP T2 minus T1. So you could do it either way, okay? But let's use that one. So we have Q will be equal to what? MA was equal to 57.122, and we had this to be equal to H2 minus H1. So before we had H1 minus H2, I lost that page. H1 minus H2 to be equal to 10.05. So H2 minus H1 will be the same thing but with a negative sign, 10.05. And this would give us a final result of Q equal to 574 kilojoules per minute. Okay, and if you want, you could actually check, because you will agree that the amount of heat going from the amount of heat lost by the air is going to be gained by the refrigerant. So you should get the same answer but with a different sign. So if you want, I'm going to put here check. Q should also be equal to what? The mass of the refrigerant times H4 minus H3. So it should be the same magnitude but with a different sign. So you can go and check on your own. Okay, so this would be the end for this video. Thank you for your time.